Oh, hello. Welcome to this example. This is example 1.7 of my classes of power system analysis dedicated for symmetrical faults. Okay. The example 1.7 is probably one of the most interesting examples in this session. And what we are doing here is we are calculating three-phase short circuit currents, but then we are planning to use that current in order to specify the circuit breaker. Okay, um, let's see what is happening here. Let's consider. Let me use this pointer. Probably is better. Consider a small industrial plant, and it has a 25 MVA 13.8 kilovolts synchronous generator, SG. You can see here it's connected to busbar number 2. And the subtransient reactance, you can see over here is 15%, okay? 15%, okay? Then the synchronous generator is connected in order to provide electricity via a two-winding step-down transformer, the transformer here between 2 and 1, to the main bus bar, and supply electricity for, in this case, for 4 identical synchronous motors. Okay, you can see here this is the 13.2 kV bus bar. Yes, here you can see that we have here the generator, and on the other side we have 6 kV. We are using motors. Yes, we are using 6.9 kV motors. Okay, that is the idea. 4 motors are identical. Each one of them is 5 MVA, 6 kV, and you can see over here. In this case, the the subtransient reactance. The subtransient reactance is equal to the subtransient reactance is equal to 20%. Okay, here there is a mistake. This is 6.9 kV. Okay, 6.9 kV, and okay, that data is provided based on the nameplate of those motors. Okay, that means that that information, that reactance is defined on 5 MVA. 5 MVA, that is the rate current, rate power, and 6.9 kV. Okay, let's put this a bit more elegant. Yeah. Okay. Okay, the step-down transformer is a three-phase unit, and in this three-phase unit, is 25 MVA and is transforming from 13.8 to 6.9, and the leakage reactance is 10%. Okay. Suddenly, there is a bolted solid three-phase short circuit at the point P. Immediately here below the underneath the circuit breaker A. Okay, this is the location for the faults. Okay, and now at the moment that that fault happened, the voltage is 6.9 kV. Okay, now considering the three-phase fault. Okay, considering the three-phase fault, what we want to do is few calculations here. Okay, one of the calculation is, okay, how much is the fault current? Okay, how much is the fault current? In this case, this is the subtransient fault current. Then we want to know what is the fault current, but in this case the fault current that is moving that is moving by the circuit breaker, okay? And also, and that is probably the most interesting part that is making this example so exciting, is we want to calculate is the symmetrical short circuit interrupting current, okay, as defined for the location of this circuit breaker, okay. Well, this is a very exciting time. Let's see. Let's start to solve this problem. The first step is that as you must recognize, the motors, they have the per unit reactance, subtransient reactance defined in the nameplate. As a consequence, the first step must be all the referring the per unit values, referring the per unit values to the same base. Okay. I believe my students are top expert in per unit. Um, but over here, you must remember what is the equation that we use. We use the old reactance multiplied by the new power base divided by the old power base. And now there is no surprise. We got here that the reactance of the subtransient reactance of the synchronous motor is 1.0. Okay. What is the next step? Okay, now what we want to do is we want to create the reactance diagram. Okay, over there you can see that we create the diagram showing the reactance. This is the reactance of the motors that we calculate here, one per unit, one motor, two, three, four motors. Then we have here the reactance coming from the step down transformer. And here we have the model, the subtransient model of the synchronous generator. You have here the internal voltage, and this is you can identify this is the subtransient reactance, okay? Okay, now we have a circuit that we can use for calculations, but before that, what I want to do is to define in per unit what is the value of the voltage um, at the fault point previous to the fault, okay? But because we are using per unit values, I need to use the classical definition, dividing the kilovolts in real units divided by the base, and this is base with B. And here you can see that this is 6.9 kV and divide by 6.9 kV, and we will get over there 1 per unit, okay? 1 per unit. Quite nice, okay? This is 0 degree because we are defining the voltage as reference at that very specific point, okay? What is the next step? Okay, the next step is very simple because what we need to do is, okay, we can use Thevenin method. We can use Thevenin method to calculate the short circuit current. And let's do that, okay? Let's do that. What I will do now is I will use Thevenin to calculate the equivalent, the short circuit current, okay? What I need to do is extremely simple. I will create the incremental network, okay? This is the bus bar number 1. Here we have one motor. Here we have the second motor. Here we have the third motor. And you must remember this is the fault point. We can say this is the fault point, okay? On the other side, we have the transformer, yes. We have the subtransient reactance from the generator. But in this case, we are creating the incremental network to calculate the Thevenin equivalent impedance, okay? What I'm trying to say is here, we are interested on calculating the Thevenin reactance. This is the transformer, 0. And this is the generator, subtransient. And this one, each one of them is 1.0, okay? I believe all my students can see that those guys are in parallel. That means this reactance here is 1.0 divided by 4, and this is the bus bar number 1. Okay, this is the bus bar number 1. Here we have this terminal, and on the other side we have here 0.15 plus 0.10, that is 0.25J. And all my clever students, they must realize that the Thevenin reactance in this case will be 0.25 in parallel with 1.0 divided by 4. Okay? Yes, that is the Thevenin equivalent. Okay? Now what we need to do is, okay, I explained to you that the Thevenin impedance will be the parallel between in this case 0.25 in parallel with 4 divided by 1 divided by 4, and I believe there is no secret when you are doing 1 divided by 4, that is 0.25. Of my students, they realize that that number is the Thevenin. Sorry, it's not focusing. Okay, the Thevenin. Now we can obtain here, you can see that the Thevenin impedance is something very simple, 0.124, okay? Very simple, okay? Now, what is the next step? Okay, the next step is extremely simple because we want to know what is the fault current. And to calculate the fault current, what we need to use is using the voltage previous to the fault divided by the Thevenin impedance, and we obtain here, and it's extremely simple to see that we obtain here that the fault current is minus 8J, okay? Okay, now the next step is let's define that current in per unit, in amps. Well, if we want the fault current, at that point, I need to multiply by the base current, okay? But in this case, the fault is happening at 6.8 kV level, and as consequence, I need to calculate the base current for that very specific voltage level. That is the reason my student must realize that I am using here at 6.9 kV. This is extremely important because I want that my students, they are aware that this base current is the low voltage side of the transformer. This is 2.09 kiloamps, and that is referred to the low voltage side, okay? In this case, I multiply the per unit value using the base, and I obtain that the current at the point P is 16 kiloamps, 16.7 kiloamps, okay? Okay, now the situation is extremely simple, extremely basic. And now what we want to do is to calculate what is the motor contribution to the generator contribution to the fault. Okay, And to calculate the motor contribution, what we need to do is simply we need to use uh, the current divider rule, okay? The current divider rule, okay? It's extremely simple. This is the generator contribution, okay? The generator contribution can be obtained by the current divider rule, and you can see something quite simple and interesting. Using the current divider rule, the total fault current is 8, and these 8, 4 per units are coming from the generator. I don't know if you follow my idea, but if the fault current is 8, and let me show you here, probably is the best, okay? I believe all of you can see this is the motor current, the generator current, okay? In this circuit, uh, we have here the bus bar number 1, yes? And the generator is contributing, yeah, with 4 per unit. And the fault at the point P, we have 8 per unit. Now the interesting question is the following. We have here 1, 2, 3, and 4 motors, okay? How much is the motor contribution to the fault? I believe all my students, they must realize 4 is coming from the generator, and the difference between 8 and 4 is coming from the motor. That means that the four motors, they are contributing each one 4 divided by 4, that is 1 per unit, each one, okay? It's simple. You have 1 here, you have 1 here, 1 here, 1 here, 1, 2, 3, 4 plus 4 equal 8, and that is Kirchhoff current law, okay? Well, that is what I want to explain now, and what I want to tell you is, okay, you can use the Kirchhoff current law if you want to make your calculations, if you want to be sure with your calculations. You can see over there that using current divider rule, you can obtain that the current moving for each motor, or providing the contribution for each motor, is 1 per unit, okay? But now the question is quite interesting, because the question two say that we want the subtransient current in the circuit breaker, okay? In the circuit breaker, okay? Now what I will do is, let me use again paper. Let me come back with my ugly handwriting, okay? What I want to show you and what I want to say is the following, okay? We have the bus bar here, bus bar number 1. We have here 1 motor, 2 motor, 3, and then we have the following, okay? Then we have the 4th motor, but the point P is located here, okay? The fault is located over there. Let me come back and do it again, because I missed the circuit breaker. This is the bus bar number 1, okay? Bus bar number 1. We have here 1 motor, 2, 3, and in this case I have the circuit breaker A, I have the point P, and then I have the motor, okay? And on the other side, I have the generator, okay? And here, when I have the fault here, this is the short circuit, the current that is going here is 8 per unit, okay? This motor is contributing with 1 per unit, this motor 1 per unit, this motor 1 per unit, this motor 1 per unit, but there is a problem. The problem is this motor there is a fault here, and this current is not affecting, to be honest, it's not affecting the current that is moving here, because the current here at the circuit breaker, this is the current that I want. The current going at the circuit breaker. Okay? Now, I believe you can see something quite interesting. Let me try to show you something about this. Let me try to do something interesting here. Give me a second. The current that we want, there is a current here, there is another current here, another current here, another current here, and that current is moving here. What I'm trying to say, what I'm trying to explain is that the current that is going through the circuit breaker will be the contribution coming from the generator and 1, 2, 3 plus 3 times the current contribution coming from the motors, okay? This is quite interesting and quite important because students, they can make this mistake, okay? Because they believe that it's 4 times, but it's not possible because this current is coming here and going to the fault, but it's not going across this circuit breaker. For that reason, the current that is moving across the circuit breaker is the contribution of the generator, the contribution coming from the from 1, 2, and 3 motors, and that is the current coming here through this circuit breaker. Okay. Okay. Uh, what I present here right now is the explanation that I did before, but now my students, they can understand this equation because I explained using my circuits. The current that is moving across the circuit breaker through the circuit breaker is the contribution coming from the generator plus 3 times the contribution of the induction from the motors. Okay. Now that current, I need that current, but using real units. And using real units, I can obtain that current at 6.9 kilovolts. That current is 14.6 kiloamps, okay? And that number is very, very important, very, very important, because you must remember that the fault short circuit level at the bus bar is 16, but the current that is moving through this circuit breaker is only 14 kiloamps, okay? Okay, probably until now, this problem has been extremely simple, and my students love this kind of problem because it's extremely simple. However, when the things start to be very interesting, it's for the final part, okay? The final part is quite interesting for many reasons, okay? And the important part here is that in this case, the interrupting current moving through the circuit breaker, it's not the instantaneous, current. The current that we calculate before, it was the subtransient current, and that is the maximum instantaneous current that will go through the circuit breaker. However, in this case, because we want to use a circuit breaker, we need to take in account that the contacts of this circuit breaker will open few cycles after the short circuit is inserted into the power system. And because we have some cycles after the short circuit, the DC component, the transient component will decrease, okay? Now, how do we take this in account? Okay, there are several ways, but if you remember, I teach you that one way to do this is to modify the reactance on the rotating machines. If you remember the EX method, the EM method say, okay, for synchronous generator, you don't affect the subtransient reactance. What I'm trying to say is for interrupting current calculations, you will use the subtransient reactance of the generators. However, in the case of motors, we need to include a factor that is 1.5 for this kind of motor, and as consequence, we know that the motor has a subtransient reactance of 1, but using this factor 1.5, and you can go and see my slides for classes. Now the transient reactance of this motor is 1.5. Okay. What that means is that right now the reactance of this motor is increased because there are some DC component that is decreasing over the time. Okay. Now, what I am presenting here is again, we have here the beautiful reactance circuit for our power system. But right now we are using 1.5 per unit as the transient reactance of these motors. Okay. What is the next step? Okay, very simple. Right now, what we need to do is again calculating Thevenin impedance. This is a straightforward procedure. All my students know now, because right now from this side is 0.25 and this side is 1.5 divided by 4, and you get 0.375. Okay. Finally, here we obtain the Thevenin impedance in per unit, 0.15. Okay. Next step, very simple. We calculate the transient fault current. And that transient fault current using the Thevenin mechanism is 6.6666 per unit. Okay. Next step. Well, the next step is calculating the generator contributions, something similar that we did before, and using the current divider rule, we can obtain the generator contribution, in this case, still 4.0 per unit. Okay. Now, what we need to do is something similar for the motors. Okay. You can use the equation that I showed you before regarding the current divider rule, and you will get now that the current contribution during the transient period is 0.66. Okay. If you remember the results, during the subtransient fault, each motor contributes with 1 per unit current. But right now, because we are at the transient period and we are calculating the interrupting current few cycles after the initial point of the fault, the contribution coming from those motors is reduced, and right now it's only 0.66. Okay. What is the next step? Well, my student must remember is extremely simple. My student must remember this equation, because if we are interested on the short circuit current that is moving through the circuit breaker, I told you early before that the circuit breaker, the current that is moving through the circuit breaker is mainly 3 times the current contribution of the motor, a single motor, and the current contribution coming from the generator. Okay. Here, that is the results at 6.6 kV. And if you remember now, for the interrupting current, this current is 12 kiloamps. But if you compare with the subtransient moment, if you remember from the subtransient moment, sorry, it was 14.6 kiloamps, and right now during the interruption time, right now during the interruption time, few cycles after, right now the current is 12.5 kiloamps. Okay? What I'm trying to teach you is that the current is decreasing, and it's decreasing because we are calculating the interrupting current. Okay? Okay, very well. Let's keep moving. And right now, the next step is the following, okay? And the next step is the following. Now, we need to try to find what is the worst case scenario for worst case scenario for the circuit breakers, okay? And if you are with me, if you understand what I would like to show you, is that the worst case scenario is when the short circuit happen, when the short circuit happen at the bus bar, and you will get the maximum fault current. Okay. In this case, I can show you the calculations here, and in real units. In real units, we are talking about that the circuit breaker at the best case, at the worst case scenario, it will be 13.9 kiloamps. Okay, considering the four current contributions going through the circuit breaker. Okay. Okay. This problem have been extremely interesting because have allowed you to identify difference between the subtransient current, and that is the momentary current for the circuit breaker, but also we spend time thinking about the short circuit current during the interrupting moment. Okay, what is the next step? Okay, the next step is probably one of the best moments. Okay, because we want to specify a circuit breaker for this system. Okay, in this case I need to use the standard. Okay, because I need to use follow the rules, and also I need to be serious about this calculation. I will be using ANSI C37.010. Okay. Um, in this case, it's known that the minimum voltage that I can find for those circuit breaker is 14.4. Okay, if you look here on the first, let me use here my pointer. Where is the pointer here? A very ugly arrow here. But if you look the first column over there, you will realize that that is the nominal voltage. The nominal voltage is, the minimum nominal voltage in that table is 14.4, okay? Then you will realize that the maximum voltage, and that is the maximum operating voltage of that circuit breaker, is 15.5 kilovolts, okay? And again, on the fourth column, you can identify a very important factor, and that is the voltage range factor. In this case, this is a bit old circuit breaker. K is a bit higher than 1. And you can see over there that in this case, this specific case, K is equal to 2.67. Okay? Okay, okay, okay. What I will do now is the following. Let me first delete all those red arrows that they are not helping me here. Sorry. Okay. Because right now what I need to do is start to do few calculations. Okay. In this case, the next step is okay. When we are working at maximum voltage, of 15 point, when we are working at the maximum voltage of 15.5 5 kilovolts, the rate short circuit interrupting current is 8.9. Okay, I believe all of you can see. I forgot to use the arrow here, but you can see that the rate current, the rate short circuit current at the maximum voltage is 8.9 for this circuit breaker. Okay. Now, if I am correct, we have all the data that we need to perform the calculations. And right now, what I will do is, let me move this a bit to the top. Okay. Now, first step. The first step is that we need to calculate what is the maximum instantaneous symmetrical current, what is the maximum instantaneous symmetrical current for this device, okay? And in this case, we know that the current is 8.9, and also we know that the factor, the voltage range factor K is 2.67, okay? Running the calculation over there, straightforward, we get over there that the maximum symmetrical interrupting capacity of this circuit breaker is 23.6 kiloamps, okay? Okay, right now we have the maximum symmetrical interrupting capacity. And now what we want to see is, okay, we know the K factor. The K factor is the voltage range factor, okay? And the voltage range factor, the voltage range factor allow me to calculate what is the lower limit, the lower operating voltage for this circuit breaker, okay? In this case, using the definition of the voltage range factor K, we divide 15.5 kV by K, that is 2.67, and we obtain that the minimum voltage that is possible to use this circuit breaker is 5.8 kilovolts. Okay. Now the interesting question is, the interesting thing is, this circuit breaker is 14.4 kV nominal voltage. Okay, that is the class for this device. And we know that this device have a maximum symmetrical interrupting capacity of 23.7 kiloamps, okay? Now the interesting question is, okay, now we are using this device at 6.9. We are using this device at 6.9 kV. Now the question is, okay, what is the capacity, the symmetrical, maximum symmetrical interrupting capacity at that voltage level? Well, what we need to do is very simple. We know that the short circuit current at rate voltage, at maximum rate voltage, is 8.9 kiloamps. And using the ratio between the maximum voltage and the voltage that we are using, we obtain over there that the maximum short circuit interrupting at that voltage level, it will be 20 kiloamps. Okay. Now the interesting question is, can we use this circuit breaker? Can we use this circuit breaker? And the answer, straightforward, is, well, we need to compare this short circuit interrupting current, I mean, the maximum symmetrical interrupting capability of this circuit breaker, with the short circuit level that we calculate before. And if you remember, when we calculate the short circuit the maximum level of short circuit level at that moment was 13.9 kiloamps. And that means that we are well below 20 kiloamps, and this breaker can be used for this specific application. Okay. Um, Again, this is probably one of the most complete problems in terms in terms of symmetrical fault analysis. Okay, here in this problem, I introduced the use of the Thevenin method for calculating the short circuit currents, the three-phase short circuit currents. Then we examine the use of some factors coefficient at the motor reactance in order to get the interrupting current. And finally, we use the ANSI C37.010 in order to estimate and verify if we can use a circuit breaker that the nominal voltage class is 14.4 kilovolts. Okay. Of course, I know that probably people coming from consultancy work or people coming from utilities, they will tell me, okay, this is very academic, but in real life, there are many other ways to do this. And I will agree with you in some very specific cases. If you know the manufacturer of the circuit breaker, they provide to you some documentation that can be used, and you can get another method to calculate the things. But in this case, this is one I want that my student have the taste and understand the basic procedure and understand the relationship between short circuit levels and specifying these kind of circuit breakers. Okay. Well, this is the end of this example. We spent almost 45 minutes solving. Thank you very much for your attention, and thank you for everything.